will be something like this. What is the other possible answer? The other possible answer will be, okay, you don't see the rest, just see the red portion. It could be something like this, inductor, capacitor. Alright, VS, okay, and finally, this is your load, RL, okay, so this one itself, it is also a filter. Second, now why is it so? Because of this one here. Now, the impedance of this, remember our summary, we said something like this, like 1 upon Z total is equal to 1 upon ZL plus 1 upon ZC, right? Now, there is a chance that where this whole thing equal and opposite. When they are equal and opposite, what is going to happen? This becomes 0, right? Agree? Now, when this becomes 0, what happens? Your Z total becomes infinity, right? In other words, it's like open circuit. Is that clear? So, when this becomes open circuit, what will happen? It is like nothing will go through your RL. This becomes a notch filter. Is that clear? This becomes a notch filter. On the other hand, if I were to put it this way, here it is my load. Okay? Now in this case, what happens? When the frequency is very low, this is the one that short circuit. So low frequency, no signal. High frequency, this is a short circuit. So high frequency, also low. Only when it's resonant. Resonant is where your impedance cancel one another. When these two are cancelling one another, it's as if that they are not there. So whatever signal will go through to your load. Is that clear? And that forms the band pass filter. Is that clear? Now, so to answer this question, learn how to draw this, or the other one, which is in the lecture notes. Is that clear? And then, how do you get your value such that this equal to this? Well, the answer is, class, this may not be the correct one, because in this case, calculate the capacity that will give them the reactance that's at this frequency. So, suggestion is you need to make use of this formula. Remember in the lecture notes? Okay, so once you have this set to 100K, sorry, 1000 hertz, 1000 hertz, give arbitrary value of C, then that will give you, that will determine your L. Is that clear? What's the problem? If let's say this one is 1000, if C I set it to 0.1 microfarad, okay? If I set C equal to say 1 microfarad, the only unknown is L, right? So based on this formula, I can work out my L. Is that clear? Is that clear?
There's no value given for, like actual value given for C.
All these values, the only two unknown is L and C, right? So what you can do is just set one, that will determine the other one. That's one possibility. Is that clear? Now the other possibility, as what I mentioned in the lecture notes, since these two are the formula, if I were to both set to 100 at that frequency, that will basically determine what this value is. Is that clear? So that is also one possibility. You can either do this or that. That's fine. Okay. Now, what's the next question? The next question is at the impedance. Work out what is your total impedance. The total impedance basically make use of this formula. Remember, this formula is also in your summary just now, which I give to you, right? Class, what is this formula here? What is this formula here? It is basically this formula. Is that clear? If you rearrange, your Z total is equal to 1 upon the total, 1 upon the 2, right? So 1 upon that, 1 upon that, 1 upon the whole thing. Is that clear? Can you see that this is actually the formula? Okay? So when the two are equal and opposite, what happens? When you add them together, it becomes 0, right? So therefore, it is whatever. So having that plus, what is going to happen? It cancels out one another. So it becomes a very nice bandpass filter. So what is the advantage? The advantage is because it is only at one particular frequency that it nearly cancels. So it becomes a very narrow selective bandpass filter. Okay? Now if your answer presented it is a notch filter, for example, then what happens? It becomes a very narrow selective notch filter. Is that clear? You understand? And what is the disadvantage? The disadvantage is mentioned here. It is because your inductor is very difficult to build an inductor, pure inductor, because it's going to have a magnetic flux altering your neighboring component and so on and so forth. So what people do is, to overcome it, people tend to, a solution is they use the so-called gyrator. Use a gyrator, which is what I mentioned in your last lecture. Alright, towards the last end, the end of the chapter 8. Okay, lecture 8. The gyrator. But what's the disadvantage of gyrator? The disadvantage of gyrator is, on the other hand, one end must always tie to ground. Okay? So some circuit may not be able to be implemented. That's in that sense. Is it okay, class? Now this is a very new tutorial question. Okay? And if you add them together, it looks like 10 marks, 3 marks, 7 marks, 20 marks. Okay? So, okay, let's go on. Now if you have a DC sensor, all right? Okay, a DC sensor whereby you have 50 and the signal reach the, well, it becomes noisy. So what do you need to do? You want to remove the 50 hertz. Alright, you have to remove the 50 hertz noise. Okay, and DC is the unwanted signal. So in other words, your wanted signal is at the low frequency. Your unwanted signal is at the higher frequency. So you can implement a low pass filter to remove it. Is that clear? So a low pass filter will look something like this. You understand? R, then C, then your load connect this way. Okay? Now, very often, this sort of question comes with drawing of your filter response. This, I believe, is a previous year's exam question, if I'm wrong. Anyways, now, when you're asked to draw your frequency response, what are the things that you need to draw at least? 4 items must be there. Passband gain, your cutoff frequency, indicating of your cutoff frequency, the gain at cutoff frequency, the slope. Is that clear? And then plus your axis. That will give you 5 points. See? Yeah. Sketch what? Typically is 5 points, right? And the 5 points typically, I already mentioned 4, right? The 5th one will be the axis. Labeling the axis. And make sure you draw your graph correctly. Is that clear? It can be high pass, low pass, sometimes band pass. Alright, so if it's on this ratio, then that will be the one. You understand? Okay. Now, the main characteristics of ideal op amp I'm not going through with you. You can just read it through yourself. Okay? It's also it's so bad. Okay, by the way, I hope my pace is okay for you all. Now, class, idea of M, I'm not going through to elaborate too much at this point. For one reason, class, all these points are listed in your lecture notes. Okay? It's also quite a popular question. If you want, you just read through. Is that clear? Nothing much I can elaborate. Is that clear? I hope by now you understand the way I lecture is when things that I think I can enhance, enrich you, I try to give it. But I only give it a certain amount of time. Certain things I need to cut. You understand? Okay? Now, okay, here it talks about connecting outputs, inverting and all this in negative feedback, and what is positive feedback, all those things, right? I hope by now, just now I already mentioned, okay? So please also note that what is positive feedback, what is negative feedback. Okay, this portion you may want to take note of. Okay? Yeah, this one I spent some time just now. Remember I draw the 3 of n there? Yeah, essentially I'm talking about this point here. Is that clear? How do you recognize what is the op amp? I mean amplifier. An amplifier it is when you have a negative feedback. Is that clear? Positive feedback it is called a latch. Okay. The advantage of that is it will somehow reduce the glitches. Okay. We don't have so much time. I'm not going through the theory of that, how it reduces. But what you can take note of, you can actually download it, right? Okay. The positive feedback allows you to reduce the noise, glitches. Alright, it can be used for comparator, ADC kind of things. Okay. Now, one more thing about your op amp is that there's this term here called gain bandwidth product. Can somebody tell me what is gain bandwidth product? Okay. This portion of this is just now what I used, right? Remember I talked about this? Okay, positive feedback. This is positive feedback, right? Positive feedback. If I were to, for example, I can connect my input like this. Down here, this becomes a non-inverting Smith trigger, for example. And what is the advantage? This one you have a dual threshold. Having a dual threshold means it can be quite stable. It reduces the noise glitches out. Alright? If you want, you can actually read out on that, which is basically covered here. Connecting the output to the non-inverting is called a positive feedback, acting this way in the opposite way of negative feedback. Positive feedback creates a conditional hysteresis, or we call it latches. Okay, but it doesn't mention what, but basically, as I say, this will allow you to have a very nice noise immunity. Alright? Okay? The others, negative feedback, note your amplifier. If it's negative feedback, your amplifier gain, please note that. And sometimes the question will give you, I want a gain of 100, a gain of 5. You need to draw your configuration. You need to work out what is your resistance value. Is that clear? Now you want to draw this or not? You want to draw it now? Make sure you know how to draw. Output connect to your negative terminal. It is amplifier. Is that clear? Output connect to your positive terminal. It is your Smith trigger. Is that clear? After that, you ask yourself where to connect your input. If my input is to your inverting terminal, it is the inverting amplifier. Is that clear? And your gain will be negative RF over R1. And so on and so forth. Is that clear now? Okay. Question 4 is still on the ideal characteristics, right? Oh yeah, this one here, we talk about, okay, for example, you want to calculate your gain in dB. How do you do it now, class?
Okay, low.
Lower down.
Yeah.
Okay, your gain in dB, how do you work on it? Okay, first of all, whatever your gain is, in this case, it will be 1 plus AV is equal to, A stands for amplification, V for voltage. Alright? 1 plus Rn over R2. R1. Is that clear? Plug in the value, you get your gain, right? How do you convert into dB? Convert into dB. Gain in dB is equal to 20 log 10 of AV. Is that clear? Now class, how would you change this so that you double your gain? The suggested answer is you double your this or half of this. Now, strictly speaking, not quite correct. Because this is a non-inverting amplifier. There is a factor of 1. So if I double this, my gain is not exactly double. Because of the 1 there. But, if you look at the ratio, this is 22K. This is 47. It's a lot more larger than 1. Is that clear? So doubling this will still more or less give you a double. You understand? Okay? So that's why I don't quite like this particular set of solution, whatever, because strictly speaking, not quite correct. Alright? But then if your intention is to roughly get something, yes, it is okay. You understand what I'm going to say? Alright? You know what I'm talking about? You have a question here. Do you agree with me? If let's say my gain is Rf over R1. Now, if this is the case, it's quite easy. Double my top, my gain will double. Or half my bottom will be double, right? But now I have a 1, you see? You understand? So even though I double the top, because I need to add 1, it's not exactly double. But then, if this term is much bigger than this 1, then the 1 is insignificant. You understand? You get the idea? This is what the assumption that this guy is assuming. Is that clear? Now, okay, since there's this thing, now there's, remember in the lecture we have this term called gain bandwidth product, right? What is gain bandwidth product? Do you still remember? Anybody can tell me what is gain bandwidth product? Now, op-amp, if you look at this, op-amp has this. Now your gain, ideal op-amp, your gain, open loop is quite high, maybe 10, let's say, whatever, maybe whatever. Let's say gain bandwidth is equal to 1 meg. Huh? Oh. It just means the exam question. Alright, look here, class. Now, if this is 0 dB, class, if let's say I tell you gain bandwidth product is 1 meg, which is 10 to the power 6, and ask you to sketch the waveform, class, can you tell me if this is 0 dB, what would be this point here? This will be 10 to the power 6. Is that correct? And let's say supposingly, let's say this is 40 dB. Can you tell me what is this point here? What is this point here? If you draw it down, what is this frequency? The answer will be now 40 dB. 40 dB is equal to 10 to the power 40 divided by 20, right? That will be 10 to the power 2. Agree?
Yes.
Now the definition of gain bandwidth product is this is your gain already, right? So what is the bandwidth? It will be equal to 10 to the power 6. So what is the bandwidth? It will be 10 to the power 6 divided by 10 to the power 2. That will give you 10 to the power 4. So this point will be 10 to the power 4. Is that clear? Clear, everybody? Alright, so what is this one graph trying to say? By the gain bandwidth product in the lecture 8, it is trying to tell you that, excuse me, I could actually use a filter, I mean, op-amp like as if it's a filter. But that's what he said. Typically, people don't use op-amp as a filter like that. Alright? But as an engineer, you need to be aware your band that you can use is not infinite. Is that clear? The bigger your gain, the lower your possible use of band because of the gain bandwidth product. You understand what I'm talking about? Alright? So gain bandwidth product has an implication that the useful bandwidth will be adjusted according to your gain of your amplifier that you are using. Is that clear? So sometimes you are asked to sketch. That's actually how you can do it. Okay? Also, okay, what are the ideal op-amp and ideal voltmeter? Ideal op-amp, ideal amp meter. Your meter is connecting to your probe of the electronic. So your resistance should be 0. On the other hand, voltmeter connect parallel to your circuit. You should not change the characteristic of the circuit. So it should be infinity. Alright? Any question? Are we done with all the questions? Yeah. So I think I will stop here and let you all ask questions if you have any. Sorry? No, as advice. No, where's the attendance list? No, class, it will be good this time round. Go through all your tutorial. Alright? Okay. Last year the IDS was very badly done. A lot of failure. This time out, I think it should not be. It should not be.
Why? Yeah.
Let's go through your tutorial. Both Dr. Sharp's portion, those error, know how to use a calculator, find standard deviation, graph, tutorial for Dr. Phil. That's quite good enough. How come nowadays so few people What happened to Alvin? So here. Lin Xinjie.